Hi there and welcome to this video on Senior Physics on Motion. In this video we're going to explore the concept of acceleration. Now we know from earlier on that acceleration is the change in velocity over time. And from this we can generate an algorithm A equals delta V over delta t, where delta V is the change in velocity and delta t is the change in time. Now delta V, or the change in velocity, can be calculated by the final velocity minus the initial velocity. Same with delta t, the final time minus the initial time. So overall we can get this algorithm. Now this algorithm, as we learned from our velocity time graphs in the previous video, basically is the gradient of the line which is generated in the velocity time graph. So we can use our velocity time graphs to interpret what's happening with the acceleration. Okay, so let's use this algorithm and have a go at a quick example. So in this example, we've got a car traveling at 5 meters per second and it speeds up to 30 meters per second in a time of 10 seconds. We've been asked to calculate the change in speed and the acceleration that's been generated by the car. Well, if you feel confident, pause the video now and have a go at those two questions. Then come back and we'll run through the answers. So pause the video now. Okay, welcome back. Well, how did you get on? So let's run through those answers. So the change in speed, as I stated, is basically the final speed minus the initial speed. Now often this can be written depending on the nomenclature that you have in the country that you're in. VF, often V subscript F, basically can be your final speed, minus VI, which is your initial speed or start speed. Here at St Hilda's we use the symbols V for final speed and U for the initial speed. So in this case the change in speed is going to be V minus U, or the final speed minus the initial speed. So as a result, our final speed is 30 meters per second and our starting speed was 5 meters per second. So I take these two away, 30 minus 5. The result is the change in speed is going to be 25 meters per second. Now my acceleration will be determined by the change in speed over the change in time. Well, I know it took 10 seconds for this change in speed to occur, so basically I can use my algorithm. Acceleration equals change in speed over change in time. I know my change in speed is 25, so I divide that by 10, and the result is my acceleration is 2.5 meters per second. Okay, I hope you did okay on that. I'm sure you did. It's fairly straightforward. Okay, so let's put this together and start looking at trying to incorporate a lot of our distance, our velocity, and then our acceleration versus time graphs. So here we've got a bouncing ball. So we're going to set our bouncing ball starting off at home. Now we're going to state that home is above the ground. So I drop my ball, hits the ground, and bounces up. Now notice that when it bounces up, it doesn't bounce as high. Remember, we've got that conservation of energy which we've got to apply. It will have lost some energy on the impact with the floor, also as it's moving through the air. So it doesn't bounce as high. Now what we want to know is what are the various graphs that are going to represent the journey that that ball took. Well, we know that it went S1, or that distance, S1, as it was falling down. We also know that as it was moving back up, it went a distance of S2, not basically reaching home. So how do we look at the graph? Well, pause the video now and see if you can determine what the distance time graph, the velocity time graph, and the accelerating versus time graph would be for each of these bouncing balls. Pause the video now. Okay, welcome back. So let's have a look and see what we get. Well, first off, we're going to look at our displacement time graph. Now, if you look at this displacement time graph, what you can see is we've got a curve which has been generated with respect to our initial S1. Well, then we get to a dotted line, a vertical dotted line, and then it curves back on itself, not reaching the same displacement from home. So what does this mean? Well, a curve on a displacement time graph means that the speed is changing. Remember, gradient is basically the velocity. Now we now see that the gradient is continually changing on that curve, so it must be accelerating. Now it accelerates until it hits the ground. Then what happens is it then changes direction and comes back on itself. So we're moving away from home. Remember, home is right at the top. We're moving away from home. We get to a certain displacement and then we change direction and come back towards home. We never actually get to home, hence that's why S2 is higher from the x-axis. Now remember, this is back to front if we're considering that home is above the ground. Now in both cases the curves are the same. This means that the gradient must be the change, or the change in speed must be the same. So now let's have a look at our velocity time graph. So look at what you've drawn and see if it represents this. Now our velocity time graph, you can see, is we've got a nice straight line which is going at a specific gradient in that first section. Well, let's interpret that. So the velocity, as we drop the ball, it's starting at 0, and as time progresses, it's speeding up. Well, it's speeding up under the influence of gravity. Gravity is grabbing hold of that ball and accelerating it downwards. Notice I use the word accelerating. Now, accelerating on the planet Earth is at a constant rate. We know it's 10 meters per second. So this incorporates the idea of force grabbing hold of the ball and accelerating it downwards at a constant rate. As a result, we get a nice straight line which is at a specific gradient which will equal 10 meters per second. It reaches maximum velocity just before it hits the ground. Just before it hits the ground, it's at maximum V, and that's at the point where we hit that first vertical dotted line. Then what happens? Well, at that point, as it begins to hit the ground, the velocity rapidly decreases to 0. For a split moment in time, the velocity of the ball is 0. It's being compressed against the ground as gravity grabs hold of it, and then its elasticity then causes it to spring back up in the opposite direction. Notice I mentioned opposite direction, hence that's why the line goes beyond the x-axis and below into the negative area. So what then happens is it's then sprung from 0, it accelerates up to its maximum speed, and then what happens is it then lifts off the ground. Now as it lifts off the ground, it's then being risen above the surface of the Earth, which means that gravity is going to be grabbing hold of it and it's going to be gradually slowing it down. Notice it's going to be slowing it down at a constant rate. So it will be decelerating until it reaches the top of S2, which is when its velocity will then equal 0. It will then accelerate downwards and we'll get a sawtooth graph with each of the points actually being smaller and smaller and smaller. So to recap, from a velocity of 0, it accelerates at a constant rate down to its maximum velocity just before it hits the ground. At that point, it then decelerates as it hits the ground, drops to 0. The elasticity then causes it to then accelerate up to its maximum speed just as it leaves the ground, and then as it leaves the ground it's then decelerating again at a constant rate of 10 meters per second up until 0 when it reaches the top of its flight. Now notice both of the gradients for the beginning section and the second section are in the same gradient. Why? Well, gravity is going to be the same. The acceleration due to gravity is going to be the same in both instances. So that's a displacement time graph. That's a velocity time graph. Now let's have a look at our acceleration versus time graph. And this is the graph we should have had. Now in the acceleration time graph, you will notice that in the first section, it's horizontal. Horizontal basically meaning it's at a constant acceleration of 9.81 meters per second or 10 meters per second, depending on what you want to utilize. Then what happens, it decelerates. The ball then decelerates down to 0. And for a split moment of time, it's not moving. Because it's not moving, there's no acceleration, there's no velocity, it's not doing anything. So that's why the line drops down to 0. It then accelerates in the same direction, basically moving back upwards again until it reaches 9.81 meters per second, which is what's going to be happening as it's decelerating as it moves back up. So we've got decelerating and then we move up to accelerating at the top. So basically that explains our displacement time graph, our velocity time graph, and our acceleration time graph which is generated. Generally we don't deal a lot with acceleration time graphs. However, if you study physics and go into looking at simple harmonic motion, or if you happen to be studying anything to do with AC and looking at units between inductors and capacitors in AC current, you then look at phase diagrams. Phase diagrams require you to produce displacement, velocity, and acceleration time graphs, so you may be able to incorporate these graphs into your various diagrams. Okay, well, I hope you found that useful. Let's look at some other little graphs that we might get represented. Now, in this case, we've got a velocity time graph, and you'll notice that the velocity time graph, as time goes on, the velocity actually becomes a constant. What does this mean? Well, basically, this is terminal velocity. Now, you may have come across terminal velocity. It's the sort of thing that you get if you jump out of an aeroplane with a parachute, hopefully. What happens if you jump out of an aeroplane? You will accelerate downwards. And eventually you'll get to a point where the friction which is generated by the air passing through you will equal your speed acceleration, and the two forces will become equal, which means you won't speed up anymore. So you basically, your friction due to the air equals the force of gravity. So if we drew an acceleration time graph for this, we get a situation that would look like this. Basically, we jump out of the aeroplane, we're accelerating at 9.81 meters per second, but as we're getting faster and faster and faster, our acceleration is beginning to decrease until eventually we reach terminal velocity. Hence, at that point, our acceleration will be zero. So I hope that sort of makes sense with respect to terminal velocity. Well, that basically concludes everything that we need to look at with respect to distance, velocity, and acceleration. I hope you found that useful. Do check out the worksheet on the post on this course, which will run through some questions on acceleration, some acceleration time graphs, and I look forward to meeting you again in our next video. Bye for now.